Okay. So today we are going to cover Raoult's law. Raoult's law. And keep replying, beta, because I don't know whether you are in a class or not. If you will reply, so I want to make communication. Okay.
Yes, sir.
Okay. So I'm going to write heading. Today's heading. It's Raoult's law. Okay. Raoult's law. Okay, see, Raoult's law, it is named after, the scientist called Marie Raoults, the French chemist. Okay, Raoult's law, the Raoult, okay, was nothing but the name of the French scientist or chemist, you can say. Okay, he was like performing the experiment on the partial vapor pressure, and he concluded his experiment. Okay, so I'm just going to write its statement first. What is Raoult's law is? So Raoult's law states that Raoult's law states that okay, a solvent's partial vapor pressure, a solvent or solution, you can say a solution solutions means of solution. Okay, or you can say a mixture also, or a mixture. Okay, that must be liquid form. That then we can like consider the vapor pressure. Okay, is equals to the Raoult's law states that a solution's partial vapor pressure, partial vapor pressure in a solution here, not solution but a solvent. No, it is solvent. So let me write solvent here. We are discussing about first solvent. Okay, or a mixture partial vapor pressure in a solution is equals to the vapor pressure of vapor pressure of pure solvent multiplied by multiplied by mole fraction of the solution. Mole fraction of solution. Okay, it is the statement of Raoult's law. So Raoult's law states that a solvent's partial vapor pressure in a solution is equals to the vapor pressure of pure solvent multiplied by mole fraction of the solution. Okay, everyone?
Yes, sir.
Yes. For solvent, see, generally what happens? Mole fraction we already discussed in last class, right? Is it, everyone?
Yes, sir.
Yes. So if we are discussing here about the solvent, okay, then here we have to take mole fraction of solvent. Okay, but if we are discussing here about the solute, then here we have to use solute. Okay, because solutions mole fraction is equals to always 1, right? We already gone through yesterday. X is equals to always 1, and which is equals to mole fraction of solvent into plus mole fraction of solute X2. right? X equals to x1 plus x2, and which is equals to 1. So whenever we are going to multiply any number by 1, there is no effect. That's why here, if you are calculating for solution, so here we have to write solvent, and if you are calculating for solute, then here we have to use solute. That's all. Therefore, mathematically we can write. Therefore, mathematically, Raoult's law can be written as okay. See, we calculate vapor pressure of the solution. So I am writing here vapor pressure is equals to P. Okay, is equals to, then we have mole fraction of solvent into P0. P0 is what? Vapor pressure of pure solvent, beta. Vapor pressure of pure solvent. Okay, this is nothing but the mathematical expression for the Raoult's law. Okay, so now we have to write where here we can write solution. Okay, P solution, P of solution is equals to what? Vapor pressure of the solution. Vapor pressure of solution. Then X of solvent. What is X? Vapor pressure of solvent. No, mole fraction of solvent. Mole fraction of solvent. Okay, then what is P0? P0 of solvent. Vapor pressure of pure solvent, beta. Vapor pressure of pure solvent. Okay, everyone. Do reply.
Nice.
You will hear any doubt?
No, sir.
Okay. Now let's discuss from the notes now. So now here, see, according to the Dalton's law of partial pressure, the total pressure of any solvent beta is equals to the vapor pressure of solute plus vapor pressure of solvent, right? Therefore, can we write total vapor pressure P is equals to P1 plus P2, right? P1 is what? What is P1? Vapor pressure of first liquid, and P2 is vapor pressure of second liquid, maybe solute and solvent, right? Generally, P2 we are covering vapor pressure of solute, and P1 we are considering vapor pressure of solvent. Okay. Therefore, can we write vapor pressure of solute means P1, solvent equals to what? It is P10. What is 0? What is P10? It is vapor pressure of pure solvent into X1. X1 is what? Mole fraction of solvent. Likewise, P2 is what? Partial vapor pressure of pure solute, you can say. So it will be P20. What is P20? Vapor pressure of pure solute into X2. What is X2? Mole fraction of solute. Okay. So now instead of here P1 and P2, can we place these value? Can we? Everyone, can we? Keep replying. Do reply, beta. I am waiting for your response.
Yes, sir.
Okay. Where it is gone. Okay. Okay, now, so here now we have P equals to that formula. Instead of P1 and P2, we have to place this value over here that we have calculated. Okay, now, by the formula of mole fraction, we know x1 plus x2 equals to x, right? Is it? We know mole fraction of solution equals to mole fraction of solvent plus mole fraction of solute. And we know which is equals to 1. Therefore, x1 plus x2 equals to 1. Now we have to calculate here for x1, but we have to replace x1. So can we write x1 equals to 1 minus x2? Can we write that? Do reply. Can we
Yes,
write
sir.
that?
Yes, sir.
Now I am going to replace that x1 from the given formula. Okay, so what is given formula? Over here, instead of that x1, we had to write that value 1 minus x2. So same here we have placed. So now we have pressure, means total pressure equals to P10 into, instead of x1, we have 1 minus x2 plus P2 into x2. Now we have to multiply that inside the bracket. So now we will get P10 into 1 will be P10 and P10 into x2 will be P10 into x2. Now from here, can we take common x2? Because here we have x2 and here also we have x2. Can we take common? Can we?
Yes, sir.
Yes. So I have taken x2 common here. Now what is remaining inside? We have P2 minus P1 because it is in minus sign. So we can write P2 minus P1. So I have written here P2 minus P10. And that extra we have here, which is plus P2. Now this is the formula. Now we have final. It is P total, or P you can write only P equals to, we have P20 minus P10 into x2. Into x2 into x2. X2 is what? X2 is what? Mole fraction of solute into P10. So this is the formula we can use for calculating vapor pressure of solution. Okay. Okay, beta.
Yes, sir.
Okay, so repeat it once and take a screenshot for the same. Wait, huh? Yeah, from here you can take screenshot for the same. Done.
Yes, sir. Done.
Repeat it once, beta, and let me know if any doubt you have. Because it may ask in exam, write the Raoult's law and derive expression for the same. Done, beta. Any doubt, everyone? Have you repeated? Shall we move further?
Yes, sir. Done.
Okay. Okay, now we have variation of vapor pressure with mole fraction of the solute. Okay. See how it varies. See, this go through this graph, beta graph. You see here, as mole fraction increases, mole fraction of solute X2 is what? It is solute beta. Okay. For ideal solution, what are ideal solution? Any idea about ideal solution? Any idea about ideal solution, everyone?
Sir, it follows Raoult. Ideal
Not-
solutions follow Raoult.
Not only Raoult's law, but all the laws like Boyle's, Charles, gases, Gay-Lussac law, Avogadro's law, all the laws. So those solutions, they obeys all the solutions law are called as ideal solution. Okay. So for ideal solution, it slightly increases beta. It is slightly increases like this. But for other solution like that curve, can you see that? Here as mole fraction increases, vapor pressure decreases. Okay, vapor pressure is decreases, right? Like this in this direction. Is it? See, here we have for ideal solution. See, P10 versus X2, it is a straight line. Okay, it shows that the total pressure, okay, or of the solution is depends on the vapor pressure of solvent, okay, and where X2 means the mole fraction of solute is not going to affect here. So here for that X2 equals to 0 beta. x2 equal to 0 for the same. Okay. Okay. Then that's why if it is 0, then it is not going to affect the vapor pressure, right? Why? Because if it is 0, so mole fraction will be always 1. Okay, if it is 1, then it is not going to change anything, because if you will multiply with 1, there is no change takes place, right? So total vapor pressure is depend on the vapor pressure of your solvent only. Then second one, see here P1 versus X1, it is again a straight line. Here P1 is 0, means the vapor pressure of solvent, okay, is 0. So total its value depends on the mole fraction of solute and mole vapor pressure of solute only, beta, only for solute. Okay, if it's X1 means mole fraction of solvent is 0, because it is not going to affect. So totally it's depend on the mole fraction of solute only. That's why it is decreases. So as mole fraction increases, means amount of solute increases, vapor pressure is decreases. It is opposite in third case. Okay, here X2 means mole fraction of solute is not going to change or affect the vapor pressure. Okay. Okay, so all these three things affects directly the vapor pressure of the solution. Now we have composition. Oh, it is not going to come. Okay, here we have the ideal solution. Ideal solution. Ideal solution obeys the Raoult's law. Then we have Gay-Lussac law, Avogadro's law, etc. At all the range of temperature, pressure, and concentration are called as what? Ideal solution. Okay. Second, no heat is evolved or absorbed. So total heat content of the system will be the same. It is not going to change. When two components forming an ideal solution are mixed together, there is no heat absorbed or released during the process or during the formation of solution. So here, change in heat energy enthalpy is always 0, because no heat is absorbed, no heat is released. So total initial energy is always equals to final energy level, right? So there is no heat exchange, you can say, for ideal solution. There is no volume change. So volume is also not going to change when two components forming, okay, an ideal solution. Okay, the volume of the ideal solution is equals to the sum of volume of the two components taken in a mixture. Okay, so change in volume will be 0. So total V1 is equals like V means volume, total volume. So I'm writing here VT is equals to V1 plus V2. There is no change, like it is not going to increase or not going to decrease. Okay. Fourth condition for ideal solution. The ideal solution, solvent, solute, or solute, or solute, solvent, or solvent interaction. Okay. Molecular interaction is incomparable, like comparable. See, their solvent, solute, solvent, and solute interaction is comparable, means they used to interact in such a way that there is no heat exchange takes place, no volume going to change. Okay, the vapor pressure of the ideal solution always lies between the vapor pressure of the pure component. Okay, see, vapor pressure of, suppose here are for solvent, okay, and for solute, okay, which is equals to always vapor pressure. V means we can write P beta, P, vapor pressure. Okay, so it lies in between here and here, in between these only, and it's almost same, not going to change much. Okay, so these are the conditions for ideal solution. Okay, so I want just repeat these conditions for ideal solution once. Repeat it once, beta. Repetition done, everyone?
Yes, sir.
Okay. Okay, now we have condition for non-ideal solution. So non-ideal point will be just opposite of the ideal solution only. So they obey Raoult's law. So non-ideal solution do not obey Raoult's law, right? Then the vapor pressure of this solution can be higher or lower than those of the pure component. It may be higher or it may be lower. Then during the formation of solution, heat may be absorbed or may be released, right? So here, change in heat energy cannot be equal. Del H is not equal to 0. It may be less or it may be more. Okay. Derivation from the Raoult's law, this solution was two types of derivation from the Raoult's. Okay, derivation from the Raoult's. Okay, here we have it a positive deviation. Positive deviation means when we are going to form the solution. Okay. So when solution in which solute and solvent intermolecular attraction are weak, okay, it is weaker than those between the solute or solvent molecules. Okay, they exhibit the positive deviation. So this is the condition beta. When positive deviation takes place, when solute solvent interaction. Okay. See, solute solvent means first, suppose here we have the solution. Okay, here we have the solvent. So there must be solvent particle and solvent particle, they are having interaction. Suppose here we have taken water, beta water. So we know there is a force of attraction was between two water molecules, right? So that force of attraction is nothing but we can say interaction between solvent and solvent particle. Okay, it is going to be weak. Okay, for suppose this is the solvent, and if we will add solute here, solute. If we will add here solute. Okay, so here solute and solute interaction we have. So when we are going to add this solute in solvent in order to form solution, these bonds are going to break and solute and solvent. Okay, interaction takes place. But if it is less better, if it is weaker, then that one and that, then deviation takes place positive. Okay, but it's if it is less than the original one, so deviation takes place negatively like this. Okay, so see here, this is the normal line, but here it takes place in a positive way like this. Okay, in second case, negative deviation. Okay, see here it is a straight line, so here it is also negative deviation, negative here. Here also, and here also negative deviation takes. Okay, because volume is going to decrease. Because if interaction is very strong between solute and solvent interaction, then their intermolecular force of attraction is more, so space will be less. If space is less, so it is going to like require less space, so volume is going to decrease. Okay. Okay. That's why it goes deviation. Okay, now we have a corrugative properties. So just read once and let me know if any doubt we have, then we will start corrugative property. Repeat it once, everything once. Okay. So now we will move further. Colligative properties now. If you are not replying, that means you don't have any doubt, right? So now we will go for colligative properties. Now, what are colligative properties means? See, whenever we are going to like check for melting point, boiling point, any measurable property of the matter, can we check only for one particular particle? Can we? Because suppose if you want to check melting point of water, okay, melting point of water. So can you go for calculating melting or boiling point of water molecule for one molecule only? Is it possible?
No, sir.
No. So we are always using bulk properties of matter. That means large number of molecules we are considering together. Okay. These large number of properties of all the particles are called as collective properties. Collective properties. Collective properties. Okay. These collective properties are nothing but the colligative properties. These are nothing but colligative properties. Colligative properties of solution. Okay. First colligative property we have lowering of vapor pressure. Lowering of vapor pressure. Then we have elevation in boiling point. Then we have depression in freezing point. And last but not the least, we have osmotic pressure. Osmotic pressure. Okay, so these four colligative properties we have in our syllabus beta. First one is lowering of vapor pressure, then elevation in boiling point, then depression in freezing point, and osmotic pressure. Okay, so first we will start now lowering of vapor pressure. So first you have to understand what is vapor pressure, and I have made you understand already. What is vapor pressure, beta? Yes, what is vapor pressure? Do reply, everyone. Rituraj, Samita, Ajay, do reply, beta. Yes, do reply. I'm waiting for reply.